Okay, so I got into this field due to Abbas, really. Some years ago, he told me about this interesting problem in X-ray diffraction, where they've developed this new machine called the X-ray free electron laser, which produced extremely bright X-rays, but in which the particles were injected into the X-ray beam in random orientations. And what is more, that we don't even know the orientations. So he's followed the path which you heard about this morning, in which one tries to determine the relative orientations of different particles corresponding to different diffraction patterns from the information in the diffraction patterns. Now, what I will describe, so we discussed this at the beginning, and I came up with a different method in which I don't actually try to determine the orientations of the individual particles. What I try to do is derive a quantity from the ensemble of diffraction patterns, which is somehow a function of the spherical harmonic expansion coefficients of the 3D diffraction volume of a single particle. So at the end of the day, we both end up with single particle diffraction volumes, for which we can phase and get 3D structures. So this is what I will be talking about today, this method. So here's the basic information that we want to get from the diffraction patterns. So think of this as being a diffraction pattern, and if this is the center of the pattern, you can consider rings around the center on which you measure intensities. Now these intensities will be a function of so this is supposed to be Q prime of Q primed phi plus delta phi, and this one is Q phi the Q phi. And the product of these two intensities, I'm sorry, this shouldn't be a square. The product of these two intensities should be given by this expression here. This forms a set of correlations. This is a correlated product of intensities at two different points. Now you also subtract the average of the intensities in order to basically get rid of the DC term, but that's a small point. Now, in addition, we calculate what's called the triple correlations. So this involves multiplying the intensity at one point and the square of the intensity at another, and this product here actually gives us extra information, I believe. So this is what the triple correlation looks like. And again, we subtract the mean of the quantities in order to get rid of the DC term. Now why is this useful? The best way to see this is to consider a 3D diffraction volume that looks something like this. And so this is a 3D diffraction volume, but nevertheless, there can be 2D evolved spheres which form saucers in this 3D diffraction volume, and one saucer can be this red saucer here, another one can be this blue saucer, and if you consider the intensities in this red saucer, it's given by this expression in terms of the spherical harmonic expansion coefficients, and the difference between that and the blue saucer is simply that you multiply the expansion coefficients by a Wigner rotation matrix, given by this expression here. So if you consider I'm just doing it for the pair correlations for now. If you consider the pair correlations, what one does is one expands each of these intensities in terms of their spherical harmonic expansion coefficients, multiplied by the rotation matrices, which are going to vary, and so this is the value of the pair correlations. Of course, they have to be integrated over all orientations of the particle, and this gives Wigner rotation matrices that vary with orientation. In addition, there are these spherical harmonic expansion coefficients, which is what we have ultimately after. Now, this means that the correlation coefficient corresponding to these 2 points here can be actually, just by doing some algebra, you can show that this is the product of a Legendre polynomial of certain angular momentum multiplied by the square, quantity b, which is roughly a square of a product of spherical harmonic expansion coefficients. Now, the important thing is this: if I were to consider q prime equal to q, then this thing just becomes the modular square of the spherical. It's the sum of the modular squares of the expansion coefficients. Now, and the whole idea is to somehow extract from the b's the spherical harmonic expansion coefficients, after which you can write the 3D diffraction volume and solve it. Now, what do these b depending on the value of q, and from these, by doing a transform or an inverse of this equation, you can extract the b's. Now, the b's are nice because they are basically products, sums of products of spherical harmonic expansion coefficients. Now, what I want to say is the following: the b's can be easily extracted from the data, and they just depend on this principal quantum number, this angular momentum quantum number L. But the right-hand side depends on an extra sum over magnetic quantum numbers. So the problem with getting the ILMs out of this is that there are more of these than there are those. But it turns out there are ways of doing this. I just tried to make something on the basis of. So what if there are multiple conformations contributing to each B? Multiple conformations. It means that the B that you measures is somehow an average over all the conformations. However, these conformations can be revealed by doing an SVD of different subsets of these diffraction patterns, of the B's from these different diffraction patterns, I believe. Let me go on. Okay, but that's for the future. Now, as I said, it's relatively easy to obtain these quantities B. But what we really want are the ILMs, because we need the ILMs in order to produce the diffraction volume, which we can then phase. Now, there are clearly cases where one can solve this equation to get the ILMs. One of these cases is where the magnetic quantum number is exactly equal to 0. And now you'd expect that for the so-called Nanorice particles. So in that case, so if the m's are equal to 0, the so-called triple correlations, I didn't show this, but it's possible to show that the triple correlations are a product of 3 spherical harmonic expansion coefficients of magnetic number, quantum number m equals 0. But they have 3 different L values. Now, the quantity on the left can be found from the experimental data. And the question is, can you find something about the quantities on the right? Well, it turns out you can, because, let me go back 1 second. Right. So if the only allowed value of m happens to be 0, then there is no sum over m here. We just put a 0 in here. And then the square root of b automatically gives you the magnitude of each of those coefficients. The only thing that's not known is the sign of those coefficients. Now, that's what I want to describe finding. Now, if you look at this expression here for the triple correlations, it's a product of 3 of these spherical harmonic expansion coefficients. And by looking at all possible combinations of 3 numbers and comparing this with the experimental quantity here, it's possible to determine all the signs. Now remember that although these look like different quantities, they're actually the same quantities varied over the different values of L and L0. So the number of unknowns here is the number of L's multiplied with the number of Q's, and the numbers of these things on the left-hand side, the known quantities, is also the number of L's multiplied by the number of Q's. So the number of equations is equal to the number of unknowns, and in principle, it's possible to solve these equations. Now, so as I said, you can construct a diffraction volume. This is a 3D diffraction intensities from a particle which has m equals 0. And this is roughly what it looks like. This is the work of my student, Sandy Vibovo. I don't know whether he's here. Never mind. So he calculated that diffraction volume, and then he ran a simple phasing algorithm, and this produced a particle of the known shape. But this is, of course, only of Nanorice, which is a very simple particle. Now, very recently, there has been this so-called single particle initiative. And the aim of this single particle initiative is to find the structures of viruses. And there have been experiments performed at the LCLS in California, where one tries to find structural particles. Now, in this case also, the diffraction volume can be written as this linear combination involving the GLs. Sorry, these quantities are known as the expansion coefficients of these things, which are called icosahedral harmonics, which are just linear combinations of spherical harmonics. They're linear combination spherical harmonics which have the angular symmetry of an icosahedron. And so the idea is to find these quantities here. Once again, these quantities here, because in this case, of course, the m values are not, it's not only m equals 0 that contributes, but the other m values are related to the first in constructing this. So the GL, the expansion coefficient of the icosahedral harmonics only depend on L. So once again, one can find the GLs by just taking the square root of the B's, and then by once again playing with this equation and looking at all possible combinations of signs, one can determine the signs of these quantities. Again, there's enough information because the number of terms on the left-hand side is equal to the number of terms on the right-hand side. Now, I just want to get back to the Nanorice case that I just considered. This is my calculations by my student Sandy Vibovo, and what he did was he calculated the B's from the multiple diffraction patterns as various numbers of diffraction patterns. So if he just used 100 diffraction patterns, he got this curve, which approaches nothing like the exact theory curve. But as he increased the number of diffraction patterns, he got closer and closer to the theory curve. Now, obviously, when you get enough convergence to the theory curve, it works. Okay. So now let me come to the case of the icosahedral virus. So in March 2015, this year, the Haidu group published a 3D virus image of experimental data from the giant Mimi virus. We obtained, Haidu, 200 good diffraction patterns that they used for their analysis. Now, this may not be enough in view of the previous slide, but we got some results from this. Now, in this case, the capsid is quite thick and probably not too different from the XFEL RDV. So if you so there's an analytic formula for a sphere, a field sphere, which is well known, and you can calculate an approximate structure of the virus from that. And in this case, that's not very different from the XFEL pictures of RDV. This is called the rice dwarf virus. These experiments were done on something called the rice dwarf virus. And we feel that this is a good set of diffraction patterns for testing our method, especially as the structure of the capsid has been published in the PDB. And since the data is available from 1,000 diffraction patterns. We simulated some diffraction patterns using the PDB coordinates And this gives a good image, as we see on the next slide. This is the, sorry, next one. This is the image we got, and you see it's an icosahedral shape, and it's roughly the size of the virus also. Now, I want to specify that the icosahedral symmetry is only an angular symmetry and says nothing about the radius of the virus. And the information about the radius of the virus is obtained purely from the data. It's not from the icosahedral approximation. Okay, so that's what we got. And then we applied this to Haidu's experimental data. If you plot so the phasing algorithm that we used ran 50 iterations of the error reduction algorithm and another 300 or so iterations of the flipping algorithm. Now, and it gave quite a good R factor in the end of about 0.25 or so. Now, so what did we get? We got something that looked roughly like this, but we need to do some more testing to be absolutely sure that this is right. So we're not going to print about this yet. So Kim actually did the calculations, and he found that this is roughly of icosahedral shape. Now, I want to point out one other thing. There's one very important feature of icosahedral harmonics, and that is there are no icosahedral harmonics between L equals 0 and L equals 6. So now, in addition, the value of Q is related to the value of L through Q times R equals L. Therefore, for the small angular momentum quantum numbers, that they will correspond to small values of Q, which means they correspond essentially to the data in the beam stop. So long as you're below L equals 6, we know that the next one down is L equals 0, and it is spherical. So below this point, we could even use the analytic formula that is well known. I think it's on the next slide. This is the well-known analytic formula for a uniform sphere, and we can, if we need to, we can fill in the data in the beam stop. So we're trying to avoid doing this, but if it's necessary, we could actually do this. Because of the properties of icosahedral harmonics. There are no icosahedral harmonics between L equals 6 and L equals 0. So this is an analytic formula for the angularly averaged amplitudes from a sphere of uniform density. Now, so this can be the L equals 0. Now, recently, there was an algorithm published in PNAS by the group from Berkeley, in which they claim that it's possible to obtain the M values even from the measured PLs. And essentially, what they do is the following. They assume some, so they take some random value of the electron density, and from that, you can always calculate an initial A0, an initial A, amplitudes ALM actually. And from them, you can calculate the intensities, coefficients, and hence the B quantities. Now, what they do is they rescale the B's to be consistent with the experimental values. This is more or less in accordance with what is done with the usual phasing algorithm. Now, with the phasing algorithm, you have the amplitude, the intensities, but you don't know the phases. So what you do, you just assign the intensities to the magnitudes and hope that through the iterations you can extract the phases. So this is what they do. They just rescale the B to whatever they get from the initial rows, and they don't know the phases, but that's okay. They just rescale the B's, but Yeah, so we have a value of argm from the previous iteration, argILM, the previous iteration. And this is taken as its value at the previous iteration, as in a usual phasing algorithm. And this specifies both the intensity and the magnitude of the amplitude, which is the square root of the intensity. And then what we do is we keep the, what they do is they keep the phase of A and calculate the density. The phase of IM is then found by increasingly localize the density in real space using the shrink wrap support. So this is what they do. They constrain the intensities to the B's, which are measured from the diffraction patterns, and they get the phases by using what's called a shrink wrap support in real space. And they claim that the magnitudes of the ILMs are found from the measured B's. Now, if this is true, this will have a great implication on the field. This is the picture that appeared in their PNAS article. So this is the original structure of some protein, and this is what they recovered with their algorithm if they applied some kind of symmetry constraint. Now, admittedly, the type of symmetry constraint is not quite icosahedral; it's just a 5-fold symmetry, but they did obtain this. And similarly, if this is the original, this is what they recovered. And if this is true, it's got tremendous implications.
How many resolution elements did they have?
I guess you have to count this. I don't know how many. Looks like a fair amount. I don't know.
Also a question, the right structure. This
the
is
middle
a
one.
construction that this seems to have a higher resolution.
This one here is higher resolution than this.
No. Well, in the bottom, I can see clearly.
The left-hand one has a hole which you can't see. That's a very small feature.
That's true.
Yeah, so this is the original, this is the reconstructed. And it's pretty good. I mean, apart from the middle one, didn't use any symmetry at all. Yeah.
Even the one calculated from PDB doesn't actually have 5-fold symmetry. It's not exactly 5-fold. You can tell from that ring.
Yeah, it's not exactly 5-fold, but maybe it's. I don't know. I can't talk to
right down the axis.
Okay, that's true.
It looks fairly 5-fold.
Actually, how do they impose the symmetries? In the ILMs?
Right, in the ILMs. Okay. So, you know, if you got 5-fold symmetry, you only got m equals 0, m equals 5, m equals 10, and so on. Okay, so they claim that they can get a structure out of it. So that is their solution to the problem that the B's do not contain M's, magnetic quantum numbers, that they only contain the principal quantum numbers. Now, I just want to say one more thing about this, and that is that...
there was a question.
Yeah, sure,
sorry,
sure.
I'm sorry.
Sure.
You can impose the symmetry, like you just said. Can you impose in this algorithm the hole? Can you impose the topology?
The topology?
Yeah, the hole in the middle. Can you force it to have a hole?
I don't know. I don't know what they did there.
Not
I think they all did.
In yours, can you? In yours?
No, but the hole is in real space.
We haven't tried.
Yeah.
Well,
okay.
Yeah.
I guess you can do it in real space.
Right? Yeah. No, but
through a support constraint.
But the support is on the B's, not on the real space. No,
the support is in real space.
Okay, but then you can have the hole, yeah.
Yeah, you can have a hole. You can impose that if you want.
Does shrink wrap work if you have a hole?
I guess you would know better.
I think it works even better.
Just developed in Arizona.
because that's what it is. It works to exclude spaces, right? If you are able to exclude something, it works even better.
It works even better.
Well, but then it won't be strained because you're expanding in the middle, right? So straining from the outside.
Yeah, I thought that shrink wrap has to have a closed support, which means it can't have a hole.
Does it? I don't know that.
No.
Does anyone know?
No, I don't say so.
I couldn't hear you. Say it again.
I don't think
compact. Sorry, I thought it had to have a compact support, which means it can't have a hole.
No, I don't think so.
No, in the shrink wrap you can.
No, I think in shrink wrap you can.
I did some phasing of like channel property, and
Oh,
then
okay.
the whole shows up in the shrink wrap. It doesn't
Okay,
have to be complex.
Now, I want to make one important point about this method, and that is that it does not seek to find the relative orientations of the particles contributing to each diffraction pattern. What it does is it finds the some function of the spherical expansion coefficients of the diffraction volume of a single particle from this collection of multiple diffraction patterns, which may have multiple particles. But it seems it does not matter too much because the method basically is based on the total intensity scattered by all the particles in the sample. So even if you've got multiple particles with random orientations, it doesn't really matter because ultimately what you're calculating are the correlations from a set of diffraction patterns of all orientations. So you never actually find the okay. The other point I wanted to make was that it is quite difficult with the current X-rays to get a signal from a single protein molecule. That's because the diameter of a typical X-ray, even the design specification, is about 100 microns. 100 nanometers, and a typical protein is much closer to maybe 50 or 100 or 10, 5 or 10 nanometers. So typical protein is usually much smaller than the typical diameter of an X-ray, and therefore it is almost inevitable that you will scatter off multiple particles in an X-ray rather than a single particle.
That has not been
true.
borne out by the latest SPI data, right?
Well, the SPI, they only look at viruses, which are huge entities. Right? Now it's true with viruses, it is possible to concentrate on one virus at a time. But with single proteins, it's difficult to see that happening because the protein is very much smaller.
Because of the dilution.
But if you make it too dilute,
You make it dilute enough that most of your snapshots are single shot, single part.
if you make
It will be noisy, but you can always.
But you do want to maximize
distribution, right? And
But
you could set the dilution to be maximum at a mean of 1. That's
yeah, but on the other hand, you do want to get the maximum signal out of the particles, and if you only scatter off one particle and a lot of empty space, you will get a very weak signal.
Yeah, but if you get multiple particles, you have the problem of having to do double phasing, so it's not immediately obvious which one's better.
I agree. This is an alternative method.
Right.
So I'm just describing an alternative method. So I finally want to end up with this application, which we found. Actually, you can do a time-resolved experiment with an X-ray free electron laser using this technique. So if you were to illuminate particles coming in a beam with a laser beam, and all the proteins from this point onwards will be in some kind of excited state. And if you were to hit it with an X-ray laser, a certain defined time after the laser excitation, you will see the state of this particle at some excited state. And similarly, and by measuring these X-ray diffraction patterns, you can get many diffraction patterns corresponding to random orientations of the particle. The fact that you're hitting multiple particles doesn't matter with this method, but you should be able to get the B's. Okay, so now what are the B's? As I said, there's an analytic formula for the B's in terms of the ILMs. And if you differentiate both sides, so you get a delta B on the left, and on the right, you have to differentiate this product, and that's a sum of these two terms. And then, but remember, ultimately, we want to get a difference electron density, rather like Maria said. So if you write this as the modular square of the amplitude, and then we take the differential of both sides of that, we get this equation, and then we can substitute that into there. We can take its angular momentum components and substitute into there, and we ultimately end up with an equation that looks something like this, which is the change in the B quantities, the quantities extracted from the correlations, multiplied by a matrix which we can calculate, multiplied by the difference electron density. So by inverting this equation, one can get the difference electron density, a little bit like Marius's experiment. But this time it will be on particles which are randomly oriented, and you can hit multiple particles which are not crystallized. So one of the advantages of the correlation function is that it filters out uncorrelated signals, e.g. from background, uncorrelated interference fringes from random deposition particles. The expected mean photon count for high resolution Shannon pixel for 100 megadalton protein we calculated was about 4 times 10 to the minus 2. But the expected value of 2 such MPCs, mean photon counts, is 1.6 times 10 to the minus 3. And the value of this product is expected to reach J. So the point is that although this seems like a very small number, you've got a million diffraction patterns that's typically measured in an X-ray electron laser. And so you multiply this by a million, you get a number that's very reasonable. And each DP will have multiple particles with perhaps 10 to the 6 diffraction patterns measured. Thus, it's possible that this method could be a practical one. Okay. Now this is a point about noise. It is true that that this depends on the correlated signal between similarly oriented particles. Now, in a general experiment, you would expect particles in random orientations. And what happens about the correlation between particles in different orientations? Now, it's true that there are more of those because there are more off-diagonal terms than diagonal terms. But the noise from this will go up as n, which is the same as the useful signal. And Kirian et al. Pointed out that the signal to noise goes as n upon n, and therefore it's independent number of particles per snapshot. However, I think Kirian et al. Ignored the fact that there is that if you average signals from different diffraction patterns, the noise in the average goes down faster than the signal, because the noise, although it's of the same magnitude as the signal, it has random signs, and therefore it averages out to a smaller number. So this is the point that made there. And finally, here are 2 calculations performed by Kanupriya Pandey. And this is for a PYP. We did some computer experiments on PYP for 1 particle, 10 particles, and 25 particles. And even up to 25 particles, we found that there was a reasonable signal. So the importance of this is that it means that we can do experiments on multiple particles randomly oriented in a solution and still recover the difference electron density, rather like what Marius talked about in crystals. If this is true, it should be possible to do this. So, of course, these are only theoretical calculations, and we have to see whether it works in practice. Let me see. Okay, so this is my conclusion slide. It's possible to think of a method of multiple correlations as a multiple particle method because it works even on multiple particles. And if so, if it's not possible to focus down to a single particle, then you do need to use the multiple particle method. However, just because it can deal with multiple randomly oriented particles, this does not qualify it as a single particle method. And in fact, we are also participating in this single particle initiative for that reason. The original XFEL derivation was for a single particle, as I said. I derived this originally working with Abbas on showing that this derivation worked for a single particle. It not only looks at the quantities which are averages over a large number of orientations, this average is the same for all particles independent of their initial orientation. So this is what makes it applicable to multiple randomly oriented particles. However, it can also be used in single particle experiments. This method can be derived for random orientations of particles in SO3, but also random orientations about a single axis. Now, I just want to end up by mentioning this single axis application because it's very important. If you're talking about membrane proteins, which have been very resistant to crystallography, it's possible to produce membrane proteins inside a membrane. Membrane is a two-dimensional object, and if you shine X-rays perpendicular to the membrane, one can get a signal from in that membrane. And if you've got certain types of proteins, such as K-channel proteins, which are randomly oriented about an axis normal to the membrane, one can recover the structure of those individual particles, even though you're illuminating multiple particles randomly oriented about that axis. So one of my other students is working on that, and she has got good results. But I don't have time to discuss this. So as far as the practical session is concerned, we are just going to show you one of the capabilities of this technique, and that is for the so-called single particle initiative. So we tried to do it with experimental data, but it didn't quite work. So we simulated some diffraction patterns from random orientations of a virus, and then just sent it to the algorithm, and out came the answer. So this is what we're going to demonstrate today. I guess I talked about everything else. Thank you.